Hey everyone, welcome back. So in this episode, we're going to begin on our type checker. So first, I fixed a bug that we have with our string literal class. This is in the primary expression file. And remember, if you're ever lost with where I am, you can just look at the bottom of the screen and see the exact file path that I'm in. I've also fixed some problems with my Vim, which just allows me to actually navigate using my fuzzy finder again. So I'll be doing that a bit more. So I'll try to slow down when I do that because it is naturally very fast. But anyway, to see the actual problem, I've changed our test/file.c just so that suppose we're trying to compile this, which is a string that contains an empty string template. That should be allowed, right? But not only empty string template, it also needs to have a new line in it. And so this should be allowed. This shouldn't cause any issues. But if we compile this, we end up with this pretty strange message, which says that there's an unexpected token in a primary expression, end of file. Well, the only end of file is at the end here, as we can see. So something's happening where we're essentially consuming all of these tokens in order to make this string. So something's going wrong. And what I figured out is I sandwiched this expression with two like skip new line things. And that's a problem. So we do want to skip a new line before, but we don't want to skip a new line before every time. And I forget the exact details, but essentially, when we skip, I'm trying to actually like really remember how this problem comes about. But essentially, because we're skipping every single time in this loop, we never... I really don't remember why this is even an issue. But essentially, the fix is we move it from here, just right after here. Because this is really where it needs to be. This is where I sort of like would have wanted it to be. So let's see if we sort of understand this. When we start with a string. And if it isn't just like a simple string, a single token that represents a whole string, then we continue. So what does that mean? We took the first string token and then what? Then we want to skip a new line because we want to skip this one, if there is one. And this will also be the same thing for multi-line strings in principle. We would then skip that new line. And then we can look at this next. Okay, I think I remember now. The issue is, this is the string end, right? This token here is the string end, but this condition was never true, even though the next token is a string end, because the next token was the new line. And so we came in here and skipped that new line, and then we made a new string that stole the string end, meaning this string never ended. That's the problem. Okay, now I remember. So by doing it this way, we take any new lines that are there, and then if the next one is an end, we just skip this loop and we're done, which is what we want. But we don't actually break anything, because every single time we make an expression, afterwards we skip the new line anyway. So we never needed to skip the previous, we just needed to do it here. So that should fix this issue now if I run this. Or did I didn't save it. It's always good to save your files before you recompile. And there we go, we actually parse this correctly. And let's actually see, it should be the first one. Yeah, it's just an empty string, which is perfect. That's exactly what it should be. Good. So now, before we start actually coding our like type system, I want to sort of talk about how I want my types to work. And for that, I'm going to go into a file we haven't written yet. So don't worry about it, you're not going to have this yet. But on the right side here, I just want to sort of showcase some stuff. So far my design is going to actually be two different classes, which is kind of strange, if I'm being honest. I haven't found a better way to sort of merge them yet. But basically, just for like the bland concept of types, we just have our specific type keywords, right? Things like booleans, characters, unsigned integers, in which case I'm calling them naturals. I'm not sure I've fully talked about this yet, but essentially, a natural number in like mathematics is just all of the positive integers. Technically, you can sometimes include 0, and in this will be one of those cases. So I just wanted like a single word to represent these types, because in C, you'd have things like unsigned int or like long int, and those are just, it's a very long like amount of typing for something so simple. So, and then you'll have other languages like Rust that will use like I32 or U32, which are pretty nice, but they're a little, I'd say if you've never seen it before, it might be hard to know exactly what that is if you're like new to coding. And something I do like about Kotlin not having primitives is all of your type names are capital, which I do really like because it enables you to do things like this. You can create an integer called int of type int, and that's totally valid because lowercase int isn't a keyword, which is super nice because variables should be lowercase. So by making all your types uppercase initially, it allows you to use those words for variables, which I do actually really like. And so that's why I'm sticking with that with mine. And so you can see some of these are actually keywords, but 2 of them aren't. Well, I should say most of these are actually keywords. There are 2 other types that I'm going to introduce. There's the any type, which is also very familiar with Kotlin, and the unit type, so same thing. So a unit you can also think of as like a none type. A unit is what's returned from a function with no return. This would be like a void in C. Essentially, you could think of unit as having a single value, which itself is unit. You could think of it as being 1. Essentially, all it's saying is we're returning control flow, meaning like if you go into a function and it returns a unit, what that means is it's returning control flow back to where it came from, which is a good thing because sometimes you do have functions that don't do that. For example, exit functions. If you call like an abort function, that's not going to return control flow, it's just going to end the program. And so that wouldn't return a unit because that wouldn't actually return anything. But most functions that even if they don't have a return type, the return type is implicitly a unit. And any, hypothetically, I would add this in the future, but essentially it's just a representation of something that can be casted to anything else. So at least for now, our only any is none, which is like a null, right? It represents a lack of data when you have an optional type. Because in my language, I'm going to have optional types be like just built into the language because it's super useful, right? So, the next thing to sort of talk about, I mean, you can see there's bools and chars, and then you have your integers and your naturals, of course, being unsigned integers, and you have your 8-bit, 16-bit, your not specified, which in our case, we're just going to compile this directly to. So the way we're going to do this, something you need to know eventually for transpiling, in C, you don't have exact width types. You sort of can if you go into standard int, then you'd have certain types like, what would it even be, like int32 tiers, it's something like that. I don't remember the exact typing, but there's a bunch of types there. But the issue is, the compiler doesn't necessarily have to give you like an int32t, and I don't even, like I said, don't take this for granted. Like, I don't think that's exactly how it's typed, but you can conceptually understand it's a type that is an integer that's 32 bits exactly. But the issue is, your compiler doesn't necessarily have to define this type. Which, that's all well and good when you're working in C, because you can do simple checks to see if it exists. But in our language, since we're transpiling down, that would probably be an issue, and we'd have to design a whole thing to make sure that works. But there's 2 other alternatives. There's, like, the least types, and there's the, like, fast types. And so, int32 is guaranteed to be a 32-bit integer. The least types are guaranteed to be able to hold at least 32 bits. Meaning, suppose you have some crazy system architecture that's like 36 bits, right? Then you would never have a 32-bit integer, but you could have a 36-bit integer. So if you said least int 32, you would actually be getting an int that is 36 bits, but it could still hold all the information of a 32-bit integer. And so these are guaranteed to exist, the least types. And they exist for 32, like 8, 16, 64. And so we're going to end up using these. The fast ones are pretty similar. They're I like how I got rid of the E because I thought it was spelled wrong. But yeah, it's guaranteed to be at least it's the same as the least types, but it's guaranteed to be the fastest of the types that follow this. This is guaranteed to be the smallest in terms of size, and this is guaranteed to be the fastest operating one for your system. And so you have a choice on which to use, but all of our types that have a specified size, a NAT8 isn't actually going to be guaranteed to be 8 bits because C doesn't have guaranteed things. So for the widest sort of portability, I'm going to define a NAT8 as it's going to be the smallest type that has the smallest unsigned integer that is at least 8 bits. Bools are going to be exactly standard bool. Char is going to be char, which is why there's no type thing. And so int 8 is going to be the least, signed integer of 8 bits, same thing. Nat and int, though, are not going to be the least types. Nat is going to directly correspond to unsigned int, and int is just going to correspond directly to int. Mostly it's just the compiler has a choice of what to define these things as. So since these are the ones we're going to use most often, so I'm just going to directly supplement that with what C would use most often. But of course you have the choice for larger things if you need them. Now, when it comes to the reals are floating types because, I'm going with this sort of math number set naming convention because there's an issue. There's floats in C, there's doubles, and there's long doubles. And like I said, I don't want to introduce a long. So I could call this something like quadruple or something, but also that might be not true because it might not... A long double isn't guaranteed to be any specific size. It's just guaranteed to be I think it's at least the size of a double, and it might be guaranteed to be more, but it's an unspecified amount more. So in order to just keep the naming real, in order to keep the naming similar, right? I'm just going to call these all real because they can represent real numbers, right? They're floating points. They have decimals. So real numbers. And unfortunately, floats and doubles and long doubles, they don't have a standard int counterpart with least. So a real 32 is going to map to a float. I think floats are guaranteed to be 32 bits by IEEE, I think. And then double will be just the normal real. Even though, here's the thing, it is actually 64 bits. So you could equally call this 64. But like I said, I don't want to introduce a long thing. So I'm going to call the long double a real 64, which is a bit misleading. The way we've done things so far is to say that it can hold at least this size. And this is technically true, because this will be at least 64. But like I said, the double is actually sort of 64. But basically, all you have to know for these is small number means smaller, bigger number means bigger, no number means sort of default middle ground type thing. And so that's just a choice I've had to make, but I think overall this is a pretty good naming convention for these types. And then similarly, because C supports complex numbers out of the box, it's guaranteed by the compiler, I'm going to also do them. And all you really need to know is a complex number in C is a struct of just 2 floats. So if you have a complex float, because complex is a I forget what it's actually exactly. It's a type qualifier or something, and you can modify things like floats or doubles or long doubles. And so similarly, we're going to have complex 32s, complex, and complex 64. And instead of actually typing complex, I just say Cplex, just so it's about the same width as the other types. Because you also don't want your types to be super long things that you have to type all the time. So then, of course, I also have a string type. And in the future, we're also going to add a few more things here, things like an array or like a struct. And so those are going to be a bit more complicated though, and for our version of the language, we don't really need it yet. And then there's going to be some useful sort of things, some like properties and methods. But the next thing to talk about is casting. So a language like Kotlin doesn't, there's like not really much implicit casting similar to Rust, where if you have an int and you try and add it to a double, it will complain. The compiler will say that that isn't valid, and you have to cast one to the other. And to me, that's just a bit too restrictive. In a language like C, you have a lot less safety, and like everything's implicitly casted unless it breaks. And that's too loosey-goosey. So this is one of the rare times I'm going to take inspiration from Java. And I'm going to say, at least for the number types, right? It's really nice for number types to sort of implicitly cast to one another. Because like 1, this is an integer, but it is also a real number. And it is, you know what I mean? Like, if you have a function that takes in a real and you pass in an integer, that should be fine, right? Like, there should be no error there. You shouldn't have to say, like, you shouldn't have to cast it just to make it work. That seems really dumb. Now, when it comes to downcasting, though, if you're trying to downcast like 1.3 as an integer, then I can understand not implicitly casting, because you're going to lose information. If you're casting 1 up to like 1.0, or if you're even casting it to a complex number as 1.0 plus 0.0i, right? You're not losing any information in this, because if you then cast it back to an integer, you'll get exactly where you started from, because it's, you know, you didn't actually lose information. I think that's also I don't know if that's necessarily guaranteed by IEEE, but I think if you have 0 in the, because it would just be like an integer mantissa or something. So I think it might be guaranteed to sort of work the way I'm talking about, but essentially, conceptually, you don't lose information, so it's fine if you just implicitly cast. It might be a bit more, you have a bit more of a choice whether or not to implicitly cast booleans up, but I'm going to. So, you know, if I say true plus 3, that's going to give me 4, because true will implicitly cast up to 1, and false would implicitly cast to 0. Sometimes that's useful, but I also don't think it's really like, I don't think it's that complicated, but of course it's your language, you have the choice. Similarly, it's really nice, this is really nice, to be able to do things like this, where you're essentially saying, shift this character up to, and it would be kind of nice. The issue is this is going to return an integer, but then you can just cast that back down to a char. But I think that's fine. Okay, so we're going to be implicitly casting all of our numbers up, and that's why our basic types here that represent these need a priority, because we need to represent the casting priority. And so bools will be casted up to chars, and the actual priority number itself is kind of arbitrary. I just chose it to sort of reflect the like types. So for example, bool and char are really small, so it's 1 to 2, and then all the naturals up to ints are just like the numbers like 10 to 20, because they're all like sort of the same, and then the floating points are like much larger, but it really doesn't matter. And of course, any will be 0, and there's another reason for that I'll get into in a moment, but that's just because it could implicitly cast up to things. And then unit and string will be -1, because I don't actually want to implicitly cast those. I'll get, like I said, this is mostly a lot of concept, so I'll get into the rest of that in a moment, but there is a big problem with languages that have type inferencing. So, for example, in Kotlin, I can just say val x equals 5, but what's the type of 5? Is 5 an int? Is 5 a long? Is 5 a real? And what the solution to this that a lot of languages have, as far as I understand, is if you then go on to use it like a real, it will change the type and it will say, okay, this should just be a real this whole time. To me, that's a lot more complicated, and I don't really like that approach. So for my type inferencing, it's going to be very simple and basic, and I think that's better. So if I say val x equals 5, by default, my x is going to be an integer. Like just this int type here. This is exactly the same as doing this. And that way, there's just, you decide on one thing, right? So if I say 5.0, then the default type is just going to be a real. And this way, you basically, because my big issue is, I feel like a type should be set in stone the moment you declare the variable. If we're having this like strict static typing system, then when I declare x, it needs a type. So for example, in my language, I can't just say val x. You have to either give it a type or a value, because the value gives it a type. Or of course, you can do both if you want. And so because of the like way that we're doing this, that's why this order is the way it is. Because you might say, it might make sense to cast from ints up to unsigned ints. But then the issue is, right? If you're doing that, then okay, let's make, if we say val x equals 5, well, 5 is unsigned, right? How about we just add the sign when you add a negative, and then that makes it a signed int? It's like, that's all well and good. But then if you try and do something like this, the default inferred type here will be a nat, and this is going to be -1, which would be some incredibly large unsigned integer, right? That's why I'm making nats a lower priority than ints. But of course, if you want a nat, you have two choices. You can just do this, you can declare it as a nat, or you can cast the value as a nat. So you do have choices. And there is another feature in other languages. You know, for example, you could do an L to specify it should be a long, or in something like Rust, you could say like I32 to say this int in this expression should be an I32. As of right now, the only way I can do that is through casting, but in the future we might come back and we might add some notation to be able to do something like that. I haven't decided on the notation though, which is why I just haven't done it, and I'm just leaving it up to casting. But also, it's sort of like a kind of niche thing. It's not really a big deal, especially when it's just so easy to just say, this is a long. And there's another reason you need that, right? You need that in a language like Rust, because if you just say, because like you can't do this, as far as I understand, you can't say set this long equal to 5, because it won't implicitly cast an int up. I think you can do this in Rust because it will infer that 5 should be a long based on how it's being used. But in our language, where we're just saying 5 is just an int, this works because the int will be casted up to the long when you assign it. So that's the type system that I'm going to be designing. Of course, you can make tweaks. Maybe you don't want implicit casting and you want something that's a bit more like Rust or like Kotlin, where you just have to actually specify all your types. Maybe you want something more like C and everything's implicitly casted to everything else. Maybe you like JavaScript a lot and you want an empty object plus an empty string to give you, or an empty array plus a string to give you an empty object or something ridiculous like that, you know? Maybe that's the language you want. And I'm not necessarily saying that a loosey-goosey type system will produce that, but hypothetically it could. And so, I guess this episode we might not even do much coding. It's really just a lot of concept that we really need to get out of the way before we actually do stuff. And so, we'll have these basic types, right? But there's some things we need on them. Like I said, we want a toolkit for all this stuff. So we want to be able to implicitly cast things. And the way this is going to work is you'll try and implicitly cast like a bool up to some other type. And if it fails, this thing returns null. So obviously, if they're the same type, you can always implicitly cast. Even if it's like an any to an any, that obviously works. And I guess another thing I want to point out, because of the way I'm doing this, if I have val x equals null, in Kotlin that's fine. Although in our language it's going to be none, not null. This isn't going to be enough information in our language, because none is going to be of type any, And at least for now, we're not going to allow we're not going to allow variables of type any. The thing is, anytime you operate on an any, you need to cast it, because how can I possibly know what an any plus 5 is, right? So the way I'm handling that is you have to cast it. Meaning, if you're trying to do this assignment, you either need to do something like this, where you're saying you're casting none to be an optional int, meaning it's the int none, or of course you have to actually give it a type, which I think is fine. It's also better because then when you're trying to read someone else's code and you see this declaration of X, you can immediately know its type. Whereas in a lot of other languages, you have to sort of look through the code and how it's used, which might be more convenient to write by a little bit, but it's overall just like much harder to read, in my opinion. Or it could be much harder to read in certain situations. Okay, so when we're implicitly casting, for example, it's pretty obvious. If they're the same, we just return it. If the priority is negative, it's null because it can't be implicitly casted. And then otherwise, we just return like if the priority is less than it. And I don't need to do less than or equal to, because we already checked the equals up here, so I can just do less than. And then there's an implicit cast up to. So this is another sort of concept. Hypothetically, if you did something like true plus true, in your language, you might want this to end up as an integer 2. Right? You might. You might want it to cast up. So sometimes you want to implicitly cast these things up to a minimum size. And that's all that function's going to do. So for example, something we're going to do is, there's bitwise operations, right? If you have true and true, well, you don't care about the like Boolean concept of this number. You care about its bits because you're doing a bitwise operation. So we're going to upcast this to a nat8 because that's the minimum, that's the same size, but it represents like the number itself, meaning the bits. So we'll implicitly upcast bools and chars when we're doing bitwise operations. You could do a similar thing when you're doing arithmetic operations, things like true minus false or whatever, and you could just assume, okay, this is actually, we should interpret this as natural subtraction. But the choice I've come across is I'm not actually going to do that. I'm going to allow true plus true is equal to true. True minus true is equal to false. I'm going to actually allow you to do like Boolean arithmetic and character arithmetic. Because obviously, something I do really like is A plus like B should give you a character with the ASCII values that are added, and it should stay as a character. And I like that. So for characters, I'm not going to implicitly cast them up. And it might be nice to just have a language that supports Boolean arithmetic. Because, for example, if you have bool 1 plus bool 2, that is going to be the same as bool 1 or bool 2. Because if you think about the truth table, right? True plus false is true, so true or false. False or true is true. If both are false, you get false. If both are true, you get true. So Boolean arithmetic can just give you these operations, which again, it's like redundant, but maybe it would be nice if you're just messing around with this algebra stuff for Booleans to just see what happens. And then if you're multiplying bool 1 times bool 2, well, that's actually going to be bool 1 and bool 2. Because true times false gives you 0. False times true gives you 0. True times true gives you 1, where they're both the same, and false times false gives you 0. And so the other operations might also have useful utility in that as well. So that's just how we're going to do it. And again, that's such a niche thing anyway. People might never end up using that, but the key idea is it like unintuitive? I don't think so. I think it's intuitive. If you add, because that's how the other types work as well. If you add a natural to a natural, you get a natural, even if the information won't fit. It won't implicitly upcast it just because it won't fit, because I can't know at compile time necessarily if it would fit all the time. So you might have information chopped off, but sometimes that's actually what you want for your calculation. So if you're adding a bool to a bool, you should get a bool back because that's what you've been using. Okay. Sometimes you want to, for example, like I said, if I have a nat and I do a plus or a minus operation on it for unary, I just want to make it signed, but I don't want to change the number of bits. So that's what this one's going to end up doing. If you have a nat 8, it's going to give you an int 8. And then sometimes you want to operate on functions. You want to operate on these two types. So like anytime you're doing a, what's the word? Binary operation, you want to guarantee that you can operate on both of these things. And for these very simple types, you can operate on something so long as it's not an any or a unit. But we also have to add other checks in the future so that we can't just do something like this. And that's what the implicit casting's for. So suppose we have an operation multiplication here. And this could be any operator though. And we have like this and this. So what should we do, right? What should we do for this? Well, we know the result should end up being a double, which in our case is a real, because what we have here is an int times a real. So the way we're going to conceptualize this is we're going to upcast one of them to the other one based on priority, right? So we get a real because a real times a real is a real. So that's how we're actually going to get the resulting type, because we're going to try upcasting. But if we then follow this process like this, and we try and upcast a real to a string or a string to a real, there is no resulting type because we can't do that cast, therefore we can't do the operation. And so that's the way I'm thinking about this. But this isn't enough to represent all of our types. So obviously I said arrays and structs, but we're not going to worry about that yet. We'll have to add that after, and hopefully we don't have to refactor too much. Also, you see I just have some helpful properties here. It's a number if its priority is between 1 and 34, and it's an integer if it's specifically between 1 and 19. So numbers include bools up to cplex. Integers also include unsigned integers, because I'm speaking mathematically here. Integers, right? They can be positive or negative. And you can operate on them, like I said. But this isn't enough to represent our types, because there's two other properties of our types, in the future at least. We only really have to worry about one of them now, and in fact we don't necessarily have to worry about either for the like subset that we're working on. Let me take a quick look at our grammar again and see exactly. We're doing a very like minimal sort of grammar, and in fact we don't have to worry about either of these yet. But in the future we're going to. So that's going to be interesting, having to figure out how I'm going to replace that. Actually, I'll just leave it here. But so, the other one was called basic type, but this is the general sort of expression type. The type, I could just call it a type, but I don't want the namespace to mess up, so I'm just calling it expression type so that it doesn't violate other things, because we're going to have type nodes in the future that are called type. And so these will have three properties. It will have the basic type, but it also has dynamic and optional, and these are booleans, because the way our types are actually going to look is something like this. So I've shown you the question mark. It's very similar to Kotlin's nullable type, except we're just calling it optional, and we're using none instead of null. But it's otherwise essentially the same thing. So an optional type can hold any like integer here, but it could also be none, and that's sort of it. And then we have some sort of safeties on that, but that's why we need the optional as part of the type. When it comes to dynamic, if you're familiar with Rust, you could think of this as like a box. But if you're familiar with C, you can just think of this as heap. It's just heap storage, essentially. Dynamic storage. And the reason I'm doing this, I've spent a very long time thinking about this, because I've been working on C for so long. C, S-E-A, I really need to change the name. So the whole idea is, how can your compiler automatically deallocate memory, right? Because allocating on the heap isn't too bad. Especially when you have your users tell you when to do it. Because originally I was just trying to allow a language that you didn't have to worry about it, but it would still do it at compile time without a garbage collector. And the issue is pointers. Because if you're just in a scope here and you allocate something, you know exactly how it was allocated, right? If you have some int pointer x is a malloc of something, and down here, the x goes out of scope, well, that's easy. You just know how to free x because you're familiar with the scope. But what happens if you set x to the result of some function in a library? Well, we have no idea if that pointer is pointing to memory on the stack, memory on the heap, memory in the data segment, etc., right? Maybe it's a file pointer or something. I mean, I guess in this case that wouldn't be the case, but you know what I mean. So the way we solve that is, I guess, the exact same way Rust did, now that I'm thinking about it. Firstly, you allow the user to choose when data goes on the heap and on the stack. And how do they choose? Well, they just modify the type. So if you have val x of type hash int, and hash is just like some syntax I've thought of, like it's sort of arbitrary, but also because when I think of data, I sort of think of like a hash, or like a hash map, or just something like that, I guess. It's not like a best representation because like a heap is nothing like that. But anyway, so if you did this, then it will allocate x on the heap, and it will set it to 5. And then automatically, when this variable goes out of scope, the memory will be deallocated. And if you're passing it into a function, you're giving ownership into a function similar to Rust, then you're passing along the fact that it's on the heap through the type, because the type will always be known. And therefore, the language can automatically deallocate memory that way. But you need to specify it as part of the type, or you'd have to store it at runtime as some information, which is less ideal. I'd rather make programmers type an extra symbol than add some memory at runtime, you know what I mean? And so this will be very similar. The biggest criticism I have of my design that I've come up with is, you'll notice for these expression types, they have the exact same methods as the basic types. But of course, they're slightly modified, because when can you implicitly cast an expression type? Well, if you're casting an optional to something that is not optional, it cannot implicitly cast that. And so as a consequence, you can't add none to 5. That's a problem, right? Like, because that makes no sense. You just can't do that. Hypothetically, I guess you could make it like none as a result, but I don't think doing it implicitly is a good idea. So you simply can't do this. For example, if you have a val x of type nullable int, and you set it to 5, and you do x plus 4, that's a problem because x is optional. I said nullable before. That's going to happen a lot. But yeah, x is optional. So what you have to do is you have to do one of the type safety things, right? You either have to assert that it isn't none, and eventually that's going to make an error of some kind. I want to do error handling kind of like Rust. I don't want to like do exceptions. I want to just like have errors in place, but that's going to take a long time. So for now, it's just going to be very C-like, and it's just going to have undefined behavior. So, but at least if there's undefined behavior, you can look back to here and say, well, this is probably where it's coming from because this is where I'm throwing safety away. But in the future, it could actually make an error that you can handle for that situation. Or, you could do something like this where if x is none, then you could do another value. Like, you'll have different options. And then you'll see, so if it's an optional and the type that we're casting to implicitly is not an optional, you can't do that. Otherwise, you want to implicitly cast the B type. And if the B type is none, then this whole thing should be none. But otherwise, we should just copy this E type and switch the B type to the implicitly casted one, right? I hope that kind of makes sense. It probably doesn't, but basically we're just giving it the new basic type to hold. And so here's a very simple copy that I've implemented here. Essentially, by default, all three things are null, and if they're null, it just takes the existing one that we already have. So these are like modifications. If you want to change one thing but keep the rest the same, then you can just pass in one and not the others. And that's how all these work. And that's why I need to define these here because I don't want to be dealing with basic types because then it gets really messy. So I'd rather do all that here. And the consequence is that we essentially have two copies of the same class almost. But they are fundamentally different. You could think of them as having a common interface, but I just haven't written that interface. And for operating on, it's a bit more complicated. Also because I'm making this work for single operations as well, basically. I paused my recording midway through, but actually I think that's probably just going to be it for this episode. I think I've talked a lot about how our type system is going to work and what we're going to do. I guess I can also sort of show you the verifier and the actual process so you have a good concept going into the next episode. If I go up into our verifier here, this is going to be our next stage, which is it's actually going to do a lot of things. My biggest issue before when making these languages is I had a lexer, a parser, and a transpiler, and the transpiler was the type system and was transpiling the C code at the same time, which was a big issue. So what we're going to do is we're going to do one pass through our AST to verify everything. Then we'll do a second pass, knowing everything ahead of time, where we can simply just write code, because that's going to make things much simpler. And if you run into more problems, you could split it up into even more stages if you want. At least for now, I'm going to do type verification in the verifier. I'm going to do like lifetime management of variables in the verifier. I'm going to do like borrow checking and ownership in the verifier. Just because in order to verify types, I need a symbol table, right? Because if you have a variable x of type int and later you use x, in order to verify the type of this expression, I need to know what x is. So I need to store variables in a symbol table anyway for this step so that I know their type. Well, when I want to verify like borrowing and things like that, I need the symbol table as well. So I may as well do all of that at once. Otherwise, you could build like a symbol table outside of things and then utilize it for both of them or something, but yeah. So one of the other problems I've run into in the past is when you have an error using the fault system in this case, the verifier, you need a node to access, right? You need something that the error surrounds. And that could be a problem. One problem that I ran into before is essentially every single function here needed to take in a node just so it could throw an error. And every helper class needed like a transpiler so it could access the faults and stuff, and it was really messy. That's why I'm splitting it up this way, where if the types themselves can't do stuff, it just returns null. It doesn't actually, doesn't have any errors. Because again, you'll have your third implementation of these methods in the verifier, and here it will call the previous ones, so the types can manage themselves, right? I don't want to have to worry about how the types work in here, I just want them to work. And so we just essentially here, if we're doing implicitly casting here, it's exactly the same as before. We just implicitly cast T1 to T2. But if it's null, then we throw an error. And then, of course, we have to return something. And I don't want to... So if there's an error, it will just return T2. Because it doesn't matter what we return, so long as it's something that doesn't break everything else and cause other errors that shouldn't happen. You could make these failures and not worry about it, but I'd rather sort of just make them errors and do this. But right, so in order to actually get the errors, you'll notice here we have an array deck of nodes, and this is like an array list, except it's more of a stack, meaning it's very efficient at adding things to the end and removing things from the end. And we have this simple field here that's node, which gets the last of these. And now if I go into our node, there'll be some modifications up here. Firstly, you see I'm storing the type as a variable. And I'm also going to be storing the expression value, but I haven't fully figured that out yet, so don't worry about it. But the idea for the expression value actually is array sizes need to be known at compile time. So once we get to arrays, I need to know the value, right? Because you could do something like this for, like, I think this will be the notation I'll use, which is like, it's an array of 3 things of type integer. But what if you have an expression like this? Because a single token, that's easy enough. But if you have something like this, that's not really simple. And what if you have a compile time constant that is equal to 5, and then you do this here? Well, again, you'd have to sort of trace the value along. And the way we're doing that is we're going to just keep track of the value, but only like the long value. If it's we don't care about complex numbers or strings or arrays as compile time constants, because at least for now, all we care about is array sizes. And perhaps maybe array indexing as well. Because if that's an example of something that we can do. If we have an array, and all of our arrays are going to have compile time constant sizes, we'll also have slices to allow runtime stuff, but don't worry about that yet. If we have an array and we do this, well, we know the size of this array and we know the compile time value of this, so we can actually do some bounds checking. The only issue is we can't do bounds checking for runtime values, but we still want to allow something like this, right? If the user enters an X from the command line, then that's we wouldn't have a compile time value. But for the numbers, for the expressions that we do have compile time values for, and that's probably a lot of things actually, we can do some bounds checking, just some basic stuff, right? And another thing this enables us to do, if we have 5 divided by 0, well, if it's a real number, that just gives you like an infinity as like an IEEE thing. But if you have the integers 5 divided by 0, that shouldn't exist. And so we obviously, again, cannot check the runtime values. But if you do this, at least now we can throw an error and be like, you're dividing by 0, and that's going to not be defined behavior, you know? So that will be why we're storing the value, but we're also storing the type. And keyword there, storing. We're storing the type as part of every node. That way, when we get to the transpiler, we already have the type information. When we transpile, we know the types of each of our nodes, and then we can write the C code accordingly. Similar, of course, with the value. And so, like before, we're going to have a verify function. I guess not like before, actually. If you saw my original guide, this would be similar to like the transpile, because we need the construct and the companion object, but we want to verify individual nodes, right? Which is why this is not in the companion object. And what verification is going to do, by default, we're just going to set the expression type to a unit. That way we don't have to like override this for anything. That way, if you're doing a bunch of like, because remember how many statements we have, right? We have statement, which is actually abstract, and then we have file statements, basic statements, and ended statements. We don't want to have to type this every single time. That'd be very boring. So by default, I'm just going to have this be the behavior. But actually, we're not going to verify by calling verify directly. Every node is also going to have a verify node. And notice this one isn't open, meaning it's final. You can't actually modify it. The behavior of this is how we're going to verify our nodes. Firstly, you're going to append this node to the end of the list of nodes. Well, the deck of nodes, the stack of nodes. And then while you're verifying, it will be there, and it will be the latest one. And that way, if there's a problem, the verifier has access to it. And then what we're going to do is, let's see, we're taking all of the parts here that are not null, that are nodes. So that this is just getting all of the nodes, the subnodes from these parts, so that we have a generic way of verifying everything. And at least for now, this is how we're going to do it until if we run into any problems. And then we're just going to verify each of them. And notice I'm calling verify node and not verify. And then we verify itself. So we're actually doing a different sort of tree traversal here. So instead of doing like depth first search where we're going down like 0, give me like space 0. Something like this, right? Instead of going from here, I guess this sort of actually is, no, this is essentially it. Basically, instead of having to verify every part ourselves, this will do it for us. And it should just work. There might be some situations where it doesn't, but it should. And then But when you go into your verify for your node, you just have access to things. So I can show you that as well, the additive expression. We don't have to say left dot, we don't have to say verify left and verify right. We just know that they will have been verified by the time we're here. And then what we can do is we can say verifier dot arithmetic operate on the left value and the right value. And so operate on is going to basically check that we can operate on a type. Arithmetic operate on is going to verify we can do arithmetic operations on that. Bitwise operate on as well. Like bitwise operate on is going to make sure you're not dealing with floating types, for example. Arithmetic operate on is going to make sure that you're not dealing with like string types, for example. And we might even add, like, we may allow string concatenation in the future using the plus operator, but we'll just have to handle that separately, which is fine. But this will get the rest of everything. And don't look too hard on the expression value thing. This is sort of how I'm going about it, but it's a lot of like writing. So what I'm going to do is I'm going to make like a custom type, I think. That's going to make all of this a lot easier, because the issue is, if we go back into node, you see here, the value is a nullable long, because what if your number isn't actually a long, right? Or if it's a string or something, then it makes sense to have nothing there. And so because it's nullable, if you're trying to add two nullable things, that's kind of an issue. So the solution I'll like make a custom class that will make it a lot easier, I think. But I think I've probably been talking long enough for this episode. Hopefully this sort of makes sense to represent where we're headed. There's a lot in the code on the right that is for my language that we haven't fully gotten to yet, but we will be getting there eventually. I just want to start with this like small subset of the grammar. And in fact, oh yeah, I haven't even added, because I don't even have optional stuff over here. But there is another decision I've made that I should probably just discuss quickly. Like I've mentioned in the past, we're going to have these sort of these optional safety operators, but I've added this one. And so what does this do? If you have x, so this is a previous one, right? Suppose you have some struct and it's x and it's optional. If you have like x question mark dot a, well, if x is null, then this returns, if x is none, this returns none. Otherwise, it will return x dot a. That's all well and good, but I'm really tired of writing out, like if tree does not equal null as a condition. That's really tiring to me. So what I'm going to implement is just this. I'm just going to have the question mark operator by itself, but it's going to conceptually mean the same thing. Because like, what does this mean? It's sort of like saying, if tree is not optional, if tree is not none, then do this thing. So tree question mark here, the question mark postfix operator by itself is just going to return true or false. And it's going to be directly equivalent to this. This tree question mark will return true if tree is not null. Or, I mean, again, in this case, not none. Because I've been with Kotlin, I like writing conditions this way, but it's a real pain to just say does not equal null all the time, or to say does equal null. And of course, you could say this to see if it is null. Actually, in our language, it's going to be this. But yeah, that's still better than saying this. You know, it's still less code if it's not null. And hypothetically, I mean, I could do something like this. I could do like a, you know, you have other choices for operators, but I'm not going to worry about that yet. And again, this is all like in the future, and I'm still sort of designing a lot of this, which is why I'd rather just make the simplified language on the left first. Let me just quickly check. Have I made any other crazy changes? Not really. Okay, so I hope you guys enjoyed this sort of conceptual discussion, but we will be getting back into coding in the next episode. I also just wanted to make an episode without, because I did say it's going to be a long time because I'm actually designing this code. So I wanted to get this episode out so I can just discuss things and get you prepared and so that there isn't like a 2-week long gap between episodes anyways. But it looks like we do have enough to start working. I'm just worried about refactoring it, because like I've shown you, these the basic type here, like this is fine, but then the expression type is like the same thing. You have a lot of the same things, and then the verifier is a lot more of the same things, sort of, which isn't too big of an issue. And I've thought of making like some sort of interface to sort of simplify things, but I don't think it actually does. I think this is just how it's going to be for now. So we'll see, right? I hope you guys enjoyed. I'll see you in the next episode where we will start coding again.